let's just revise. Let's just go over for a second time these 4 questions that arise quite naturally when we're regressing on multiple predictor variables. We are, of course, referring to the variables that we typically denote by x1, x2, until xp. And as always, uppercase Y is the variable that we're trying to predict. We're regressing on the P predictor variables. We're looking for a relationship, and we're assuming that it is linear in nature. Yesterday, we kind of took a break from the theory. I do encourage those of you who weren't able to make it to watch our session where we focused entirely on coding, starting from simple linear regression with a single predictor variable, and moving on to using the same function in R, the LM function, but including more than one variable using the addition character. Has nothing to do with primary school addition, with the addition of 2 real numbers. And also, if we choose to do so, including interaction terms. So not looking at, for instance, if I had to invent an example right now, temperature and ice cream sales, as in that example of the shark attacks, but also taking a third variable that kind of combines the synergies, if you will, between temperatures and ice cream sales. What are the 4 questions? Is at least one of the predictors from x1 to xp useful in predicting the response? The second question, if you answer number 1 in the affirmative, then the second question is, do all the predictors help to explain why? Or is only a subset of the predictors useful? We'll remind ourselves over here of this example, our first multiple linear regression model, where the data seems to suggest that we can actually exclude newspaper advertising budget with practically a negligible slope coefficient. On its own, that's not enough. You need to compare to its standard error. You divide to create what we refer to as the T statistic, and then calculate the probability of getting such a T statistic. The higher this p-value is, the more likely you are to not reject the null hypothesis. The null hypothesis is that the slope parameter is 0. So that would be one case where, to go back to these 4 questions, only a subset of the predictors is useful. You would exclude certain variables. How well does the model fit the data? And given a set of predictor values, what response value should we predict, and how accurate is our prediction? Okay. This was 2 sessions ago, where we're now calculating the F statistic. You're looking at all the different beta parameters from beta 1 to beta p. So this excludes the intercept parameter, by the way. No, we're not really interested in that. That doesn't really tell us anything about if there's a relationship between your response and your input variable. You calculate the F statistic, and we've done it for this model over here, where we get 570. And it would just so happen that in this specific case, with our 200 observations, the book concludes, I don't think it gives any hard data, but the book concludes that this F statistic is far larger than 1, providing compelling evidence against the null hypothesis H naught. H naught is where we would conclude that there is no relationship between the response Y and any of the predictor variables. You then try and see if, probably it might be easier to just read, but you're looking at a subset over here. Instead of looking for from beta 1 to beta p, we're taking q parameters. You can do the usual p minus this plus 1 to see how many terms there are, and everything would zeroize with the exception of q. So there are q of these slope or parameter estimators. We are testing H naught, that all the coefficients are 0. Sometimes we want to test that a particular subset, size q of them are 0. This corresponds to a null hypothesis where now H naught only has q of these betas. Yep, so for convenience, we have put the variables chosen for omission at the end of the list. In this case, we fit a second model that uses all the variables except those last q. So what you're doing is you're saying, can I do without these q variables? So you fit a model that uses all the variables except those q, and you now see if this F statistic is indicative of whether you can reject the null hypothesis. I appreciate it's a lot to take in, but let's just go over it once, and we can always repeat these things in future sessions. In fact, I may choose to skip this entirely. Given these individual p-values for each variable, why do we need to look at the overall F statistic? After all, it seems likely that if any one of the p-values for the individual variables is very small, then at least one of the predictors is related to the response. Let's see. Although this doesn't look like a really concrete example, but I'll read it. I'll read it just in case. For instance, consider an example where p is 100. So that's the full extent of your data. You have your response variable y, and for each observation, not only do you have the y, but you have 100 characteristics. You've measured them, right? 100 characteristics for each observation. So if you think of it as a database, you'd have 101 columns. Think of the first 100 being your predictor variables, or you may take them, you may consider them as predictor variables. Some of them are going to be negligent or explained by other variables depending on the correlation. And then your final column, your 101st, that's the variable that you're trying to predict. And the null hypothesis that each of the parameters is 0 is true. So what would this mean? This would mean that no variable is truly associated with the response. In this situation, about 5% of the p-values associated with each variable of the type shown in table 3.4 will be below 0.05 by chance. Right. So we've often taken the example of just the legal system. Now, how does the legal system work? Well, if it's a criminal case, then we've often mentioned you are found guilty. So your null hypothesis is that the defendant is innocent. He or she are only considered guilty if, and it's a phrase we're all familiar with, if they are found guilty beyond a reasonable doubt. And this is usually where defense lawyers really excel, right? That if it's a jury system, for instance, as in our own country, I guess the expression is you're trying to sow doubt in at least one juror, and then maybe when they go in for deliberation, that one juror will convince enough of them, enough of their peers to actually err on the side of caution, the null hypothesis, and actually acquit the defendant. Now, the thing is this, that beyond reasonable doubt doesn't mean that you are 100% sure. In fact, we are really never 100% sure about anything. The example is Russell's teapot. There may be a teapot orbiting Earth. There may be. We cannot, it has to do with proving a negative. You can't really prove a negative, can you? You can't really prove that there is not a teapot. But I would say we're all fairly confident that there isn't a teapot orbiting. Well, maybe these days with space debris, Russell's teapot predates the space age. But going back to the legal system, let's say beyond the reasonable doubt is that you're 80% certain. You're 80% certain. But that actually means that given enough court cases, given for instance 10,000 court cases, then statistically you're actually only going to get 80% of those correct. And this is what we're saying over here. Remember, when we do these p-values, for instance, why not look at the code that we got up till here, right, yesterday, where we were looking at, does it quickly count them for us? Does it tell us how many? It must be typed somewhere, surely. But anyway, we had all these I ignore intercept, right? We had these predictor variables, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 of them. It's not quite 100 like the book is inviting us to consider. And the thing is this, so let's say that you reject let's say you reject this one. Well, reject isn't. But look at this. No, it's maybe a bit. It's not high enough. let's take this one. Let's take this one. This is practically 1%, right? 0.01. So if you're working with a 99% confidence interval, if this was 1%, it's a bit lower than that, but if it was 1%, then you might conclude that, taking a different color, that we may consider the true value to be 0 over here. Remember, these are estimates. Then you need to see kind of how statistically significant they are. Where you have 3 asterisks and 2 asterisks, that's statistically significant up to 1%. Although I'm kind of ignoring these 2 asterisks and I'm saying this is 1%. Now the thing is this. You are not 100% confident. It may very well be the case that, and this will happen with more and more of these predictor variables, that the more predictor variables you have, the higher the chances that just by random chance, although there really isn't a relationship between one of these variables and the response, that by random chance, the data will still indicate that there is a relationship. I don't know if this makes sense to us. Hopefully, I've kind of maybe given us a slightly better way of, a simpler way of looking at this. Let's read it, and we'll see what we're saying. For instance, consider an example in which p equals 100, and the null hypothesis is true. So no variable is truly associated with the response. Okay, so we're playing God over here. We know that. You usually don't, even the way we treat the null hypothesis, we say either we reject it or we don't reject it. But we never say we accept it. We talk about rejecting and not rejecting. Now, in this situation, if you're using a 95% confidence interval, 5% of the p-values associated with each variable will be below 0.05 by chance. And remember, and the expression is, I think a memorable way of remembering whether you reject or you don't reject is, if p is low, then h naught must go. If p is low, then h naught must go. So out of 100 t statistics, one for each variable, we expect to see approximately 5 small lower than 0.05 p-values, even in the absence of any true association between the predictors and the response. In fact, we are almost guaranteed that we will observe at least one p-value below 0.05 by chance. And this reminds me of a comic. What's that comic? XKCD p-value? What does that have to do with beans? That's not the one. Let's go into images. Yeah, this is the one. This is the one. Look. Hopefully, but I'd like to zoom. Do you open it in a new tab? Yeah, look. So look, this is your hypothesis. Jelly beans cause acne. So you're going to collect your data, and hopefully at this point, we're easily seeing what the predictor variable is and what the response variable is. There's a clear, the way it's being phrased is a clear causal direction. Jelly beans cause acne. Okay, scientists investigate. Playing Minecraft, but after a while, now they come up with this conclusion. We found no link between jelly beans and acne. So P is greater than 5%. So we're not saying if P is low, H naught must go. It's the opposite. P is not low, P is greater than 0.05%. So you do not reject H naught. Remember, H naught is that kind of the innocent before, innocent before being proven guilty. Now, this is pretty cool. That settles that, but then, okay, you're refining the hypothesis. I hear it's only a certain color that causes it. Again, scientists assemble and look at this. This is really talk about effectively communicating the whole idea of a p-value. So purple jelly beans, P is greater than 5%, brown greater than 5%, pink, same, blue, same, teal, and keeps on going on this way, salmon, red, etc., etc. And there are 20 of these, right? I would imagine. 1, 2, 3, 4, 5 by 4. There are 20. So what the book is saying is that out of 20, what is 5% of 20? It's 1, right? A 5% chance is 5 on 100, which translates to a 1 in 20. By the way, Solvency II, we speak of 1 in a 200-year event. So if a company is capitalized with enough capital as determined by the current Solvency II regime, theoretically, then it should only fail. Then from all the companies with sufficient capitalization, then only 1 in 200 of them should fail within the next 12 months. And look what the comic does. This is genius, isn't it? The comic, look at this one. We found a link between green jelly beans and acne. If P is low, then H naught must go. And this this is usually universities and these research institutes. They have like their PR teams. So imagine them on LinkedIn. News: green jelly beans linked to acne, 95% confidence, only 5% chance of coincidence, etc., etc., etc. So what's going on over here? Is there really a link? Maybe. Of course, the article is extremely tongue-in-cheek. This comic is extremely tongue-in-cheek, as most of XKCD's work is. But the idea is that just because your P is low, it doesn't mean it doesn't mean that in fact there really is a relationship. All you can really say is that we do not reject H naught at the 95% confidence interval. Now, what's really interesting over here is that kind of we've carved our data. We had an original data set and we carved it into 20 different colors. And if only, I mean, who knows? And this is the thing with statistical learning, you never really know. And I think it takes great humility on our part when we're modeling to accept that. I would put it this way: models give us a certain degree of confidence, but it's definitely it's definitely not 100%, and you can always refine your model. Think of, for example, Newtonian mechanics, and then along comes special relativity and general relativity. So you're looking at Newtonian mechanics does a very good job at describing the universe on certain scales. So planet-sized objects, for example. But when you get to maybe Mercury being extremely close to the sun, and there's such a mass differential between those two bodies, that's when the observations that the predictions that classical mechanics makes about how Mercury should be orbiting the sun starts breaking down, and the data starts deviating from what the theory, what the model, right? It's a model, what the model predicts, and that's when you can refine it. Yeah, start thinking of space-time, start thinking of general relativity. Speaking of modeling and etc., probably won't get what I'm looking for, but if you're familiar with the LSAT, which is what they use in definitely the US to get into law school. I'm trying to find the breakdown. I definitely saw one where if you have like a statistics background, it's usually some of the top performing students. I wonder if if I do, I mean, statistics is too broad of a field. What if I do mathematics? Yeah. So LSAT is specifically to get into law school. If what was the term that they use in the US? Not a solicitor, an attorney, right? And look, it really shouldn't surprise us that some of the top scoring, so you have your 150s or your high 150s and your 160s, or by individuals that have a mathematics background, a physics background. It's everything is about modeling. So it's no different. It's no different if you work in the judicial system. It's all about taking the facts, taking the data. Yeah, there might be a bit of spin, maybe focusing, maybe emphasizing aspects over other parts. But this is a course where doing this book, preparing for actuarial exams, really gives you a good feel for most things in life. Remember, even it's just that anthropological concept that what really distinguishes us from a large chunk of the animal kingdom is this so-called actuarial intelligence. Okay, so in other words, we expect to see approximately 5 small p-values, even in the absence of any true association between the predictors and the response. In fact, we are almost guaranteed that we will observe at least one p-value below 0.05 by chance. Hence, if we use the individual t-statistics, and associated p-values in order to decide whether or not there is any association between the variables and the response, there is a very high chance that we will incorrectly conclude that there is a relationship. However, the F statistic, so what's going on over here? What are we saying? I'll zoom out again and go back to the lab section. We do not look at these individual T statistics, well, this column and their associated p-values. Instead, we look at the F statistic and its associated p-value. The F statistic takes everything at one go. It's one single statistic. Instead of looking at these individually, because the risk is the more parameters you have, the more likely it is that just by random chance, you're going to get, incorrectly, I must add, you're going to get p-values that might look significant, but in actual fact, it's down to random error. Hence, if H naught is true, so if the null hypothesis is true, so that would mean that there is no relationship between the response variable and any of the predictor variables. There is only a 5% chance that the F statistic will result in a p-value below 0.05, regardless of the number of predictors. So using only one statistic, using this F statistic, there is always a 5% chance. But however many predictor variables, whereas if you had to do it on each predictor variable, then it goes up, it can go up to 100% chance, which is what we mean by guaranteed or almost guaranteed. Just because, you know, that comic used 20 kind of situations. This is using 100 predictor variables. The approach of using an F statistic to test for any association between the predictors and the response works when P is relatively small, and certainly small compared to N. However, sometimes we have a very large number of variables. This is very rare. If P is greater than N, then there are more coefficients beta j to estimate than observations from which to estimate them. In this case, we cannot even fit the multiple linear regression model using least squares, so the F statistic cannot be used. And neither can most of the other concepts that we have seen so far in this chapter, right? Normally you would have many more observations than predictor variables. When P is large, some of the approaches discussed in the next section, such as forward selection, can be used. This high dimensional setting is discussed in greater detail in chapter 6. Okay, second question. Deciding on important variables. As discussed in the previous section, the first step in a multiple regression analysis, and let's just remind ourselves what we're doing in multiple regression. Multiple regression is you're doing something like this. This diagram is really the number of the highest number of variables that we can hope to include in a diagram. We're using up all 3 dimensions that our brain kind of is able to visualize. 2 predictor variables. Notice we've ditched the newspaper variable for reasons explained earlier. We're regressing sales on these 2. And we fit a plane in which way? In the usual least squares approach where we're minimizing the residual sum of errors. Think of your partial derivatives. Think of finding turning points on a curve, but this is instead the residual sum of errors would be a function of beta naught, beta TV, and beta radio. Let's go back. So that diagram that we just looked at, that's just, when you see multiple regression analysis, just think of that diagram. Certainly the one that I think of to this day. So the first step is to compute the F statistic and to examine the associated p-value. If we conclude on the basis of that p-value, and you calculate the probability using an F distribution, so not a normal distribution, not a binomial distribution, not a uniform distribution, not a T distribution, but an F distribution. F distribution is based on two variables. Did I say variables? I should have said degrees of freedom. If you want to generate, I don't know, 10,000 of them, just say RF, lowercase f, don't ask me why. First degree of freedom, I'm just inventing numbers, 50, second degree of freedom, 10. Once you choose your 50 and 10, you're working with a specific F distribution. In statistics, it is, you're probably going to have study units, some of you, next year in your second year of university. Study units themselves might have the word family or families in the title. Families of random variables. This is an F random variable, uppercase F, in R we write it lowercase, and we can generate 10,000 of these. You could look at a histogram, but we first need to save, just like raw data. Now we can do histogram. So that's your F distribution. There is a way of calculating the, for example, the 95th quartile. And that will give you your kind of your cutoff for confidence intervals. If we conclude on the basis of that p-value that at least one of the predictors is related to the response, then it is natural to wonder which are the guilty ones. Guilty in the best way possible. Guilty in the sense, which are those predictors that are in fact related to the response. We could look at the individual p-values, as in table 3.4. This one, these p-values. So you'd get an F statistic that says that, yeah, there is a relationship between at least one of these and the sales variable. But then you need to see, okay, are they all relevant? For example, newspaper, as we've already discussed, might not be relevant. You can just remove it from your model. And what have we just said? If P is large, we are likely to make some false discoveries. Just think of that XKCD comic. It is possible that all of the predictors are associated with the response, but it is more often the case that the response is only related to a subset of the predictors. So one way of doing it would be removing some of them, running the model again. Let's have a look. the task of determining which predictors are associated with the response in order to fit a single model involving only those predictors is referred to as variable selection. So which variables do we keep? Which do we maybe exclude from the model? The variable selection problem is studied extensively in chapter 6. And so here we will provide only a brief outline of some classical approaches. Ideally, we would like to perform variable selection by trying out a lot of different models, each containing a different subset of the predictors. So this is like kind of like brute force, right? And we're going to see that the problem, not the problem maybe, but the just the computational energy required to do this, it increases exponentially with the number of variables that you have available in your data set. For instance, if p equals 2, then we can consider 4 models. Number 1, a model containing no variables. 2, a model containing x1 only. 3, a model containing x2 only. And 4, a model containing x1 and x2. So think of this as you either switch on or switch off each variable. So immediately from just thinking of this along combinatorial lines, it would be 2 to the power of the number of variables that you have available. We can then select the best model, italicized, as one would expect, out of all the models that we have considered. How do we determine which model is best? Various statistics can be used to judge the quality of the model. These include Mallow's CP, a Keiki information criterion. This is the one I'm most familiar with, the AIC, Bayesian information criterion, BIC, and adjusted R-squared. These are discussed in more detail in chapter 6, where we do variable selection. We can also determine which model is best by plotting various model outputs, such as the residuals, in order to search for patterns. Unfortunately, there are a total of 2 to the p models that contain subsets of p variables. By the way, it's like Pascal's triangle, right? Pascal's triangle, if you sum the values in each row, you get 2 to the power of. So for example, 1 plus 3 plus 3 plus 3 is 8. That's 2 cubed. This would be 2 to the 4. This would be 2 to the 5. Why? Because let's say you have 5 variables. Then there is one model that uses all 5 of them. There are 5 different models that use 4 out of 5 of them, 10 that use 3 out of 5 of them, 10 that use 2 out of 5 of them, 5 models that each use 1 out of the 5 variables. So this would be simple linear regression. And I don't even know if we should count this. This model that uses none of the predictor variables. Of course, if you're not using any of them, you don't have much of a model to begin with. For instance, so this means that even for moderate p, trying out every possible subset of the predictors is infeasible. For instance, we saw that if p is 2, it's quite manageable, right? 4 models to consider. If p is 30, then we must consider 1 billion models. This is not practical. Therefore, unless p is very small, we cannot consider all 2 to the p models, and instead we need an automated and efficient approach to choose a smaller set of models to consider. There are 3 classical approaches. There's forward selection. So you start with a null model. Okay, apparently you can have it's a model that contains an intercept but no predictors. We then fit p-simple linear regressions, interesting, and add to the null model the variable that results in the lowest RSS. Then we add to that model the variable that results in the lowest RSS for the new 2-variable model. This approach is continued until some stopping rule is satisfied. Cool, right? Backward selection, well, you go backwards, you start with all the variables, and then you start taking them out one by one. Mixed selection, we can look at it when we do chapter 6. Three, model fit. 2 of the most common numerical measures of model fit are the residual standard error and R squared. Now, we're paying the price. When we had done this was the one subsection that we had skipped in simple linear regression. I might choose to skip this over here as well for the time being. I've skipped it. If you don't mind, let's skip it. Let's go on to the 4th and final consideration, predictions. Once we have fit the multiple regression model, it is straightforward to apply, God knows what 3.21 was. It's probably just the formula, right? In order to predict the response y on the basis of a set of values for the predictors, those. However, there are 3 sorts of uncertainty associated with this prediction. The coefficient estimates, and we have that hat, are estimates for beta naught to beta p. That is, the least squares plane is only an estimate for the true population regression plane. So you're assuming that there is a true plane, but yours is only a least squares plane. It's an approximation. The inaccuracy in the coefficient estimates is related to the reducible error. We can compute a confidence interval in order to determine how close y hat will be to f of x. F of x is the true relationship. Y hat is the prediction. Of course, in practice, assuming a linear model for f of x is almost always an approximation of reality. So there is an additional source of potentially reducible error, which we call model bias. So when we use a linear model, we are in fact estimating the best linear approximation to the true surface. However, here we will ignore this discrepancy. This is a chapter on linear regression, right? So we'll ignore this and operate as if the linear model were correct. Even if we knew f of x, that is, even if we knew the true values for beta naught, beta 1, beta p, the response value cannot be predicted perfectly because of the random error epsilon in the model. In chapter 2, we refer to this as the irreducible error. How much will y vary from y hat? We use prediction intervals to answer this question. predictor intervals are always wider than confidence intervals. And I'm stop for a second. I think this answers the question we had yesterday. When we were predicting, it was one of the last things we did. It was where we were predicting, and we had C0. No, I think it was like 5, 10, 15. Because I could probably just search this, right? Just give it a few seconds. Oh yeah, here we go. So look, let me close this. Yesterday, after we fit our data, after we create this LM, this linear model, this multiple regression model, then we were predicting. And there are two types of predictions. There's where you say interval equals confidence and interval equals prediction. I'm not saying we need to understand exactly what they are today. They're definitely more than enough time in future sessions. But the idea is that your predictions are going to be off because of two sources of error. First source of error is your parameters are only estimates. And second source of error is there is an error term. Your model does not give you the error term. In chapter 2, we refer to this as the irreducible error. How much will y vary from y hat? We use prediction intervals to answer this question. Prediction intervals are always wider than confidence intervals because they incorporate both the error in the estimate for f of x, the reducible error. Why reducible? Because you can always improve your model. You can actually reduce that error. You can get betas that are beta hats that are closer than your previously calculated beta hats to the true beta. And the uncertainty as to how much an individual point will differ from the population regression plane. That's the irreducible error. We use a confidence. Oh, yeah.
Can you repeat what the prediction interval is?
Yes, what is the prediction interval? So the prediction interval, let's have a look. Let's have a look at what we did yesterday when we were predicting. And let's see how long it takes me this time around to actually... Yeah, here we go. So you've estimated, let's see. You've estimated a beta naught and a beta 1. A beta naught and a beta 1, meaning your y hat is 34.5538. plus, or in this case minus, 0.95x. So that's your formula. That's your formula. It's just y hat. It's just y hat. Let me put it over here. Okay, x is whatever, age, you name it. Now, let's say you want to estimate y. When x is 5, also when x is 10, and also when x is 15. You substitute 3 times, and you get these 3 values. Yeah, right? So look, this is practically 1. 34 minus 1 times 5 is 29.8. Then it goes down by around 5, and goes down by around 5 again, because the input is going up by 5, and the gradient is basically -1. Now, that's not enough. That's not enough. You can't just say, I know with 100% certainty that when my x is 5, when my x is 5, that my y hat is going to be 21.8. No, you don't know that. You don't know that. That might be your expected. On average, when x is 5, remember, there are other things at play. There are other variables at play. This is kind of like what that comic was doing, tongue-in-cheek, saying, okay, but if besides looking at the food item, jelly beans, what if maybe the color adds? Now, of course, in that comic, the color probably wasn't. You don't know. You don't know for certain. So what you do is you create these intervals. You say, well, 29.8, but there's kind of a lower estimate of 29.01 and an upper estimate of 30.6. Now, when you tell R interval equals confidence, this depends entirely on the error that you believe, or it depends on the extent of the error that you believe is present in your estimated betas. You never know the true beta. Even if you know it, you wouldn't know that you know it. If you tell our prediction, you get the same expected outputs. 5, 10, 15 should give you 29, 25, 20. But now we're getting a much wider interval, for the simple reason that besides looking at the extent of the error that might be in your estimated parameters, you are also allowing for the error term, for epsilon. So that's why if it's a prediction interval as opposed to a confidence interval, it's a lot wider. And when we say random error, must be a way of zooming out. When we say random error, we simply mean, if you go back, sorry. If you go back to that diagram that we spent so many lessons on, this one, the red is the true relationship. But there is a random error term, which means that the points don't all line up on the red, but they are most of them are either above or below. your model is only trying to relate y to x. There'll be these could just be measurement errors, by the way. It could just be, you're reading from a ruler, but usually that random error term is there because your model doesn't look at all the variables. So I can't say if a student studies 5 hours a day, they're going to get a grade A in their exam in 5 months' time. Well, yeah, maybe. I mean, maybe most of them. But have you allowed for other factors? I don't know. The the studying, the 5 hours a day. Is it the student that's always doing the same topic? They're obsessed with complex numbers. So every day 5 hours, yeah, but just complex numbers. You haven't taken into account that variable, the 5 hours on what are they spent. And yeah, maybe IQ, although IQ is for the most part pseudoscience, and so many other variables. Language, for example, I know quite a few actuaries. English is not their first language, and they sat the actuarial exams in English. May have been at a disadvantage, for example. And then it depends. Is there native language close to English? Is it German or Dutch, for instance, or is it Arabic? I don't know if that helps.
Yes, it does. Thank you.
Thank you. We use a confidence interval to quantify the uncertainty surrounding the average sales over a large number of cities. For example, given that $100,000 is spent on TV advertising and $20,000 is spent on radio advertising in each city, the 90% confidence interval is, and this is going to be the units of sales. This is going to be the units of sales. So what we're saying is, what do we say? 100,000 and 20,000, 100,000 and 20,000. What does the model do? The model finds 100,000 on the TV. It finds 20,000 on the radio. Gets the input $100,000, comma $20,000. Goes up or down. Over here, you have to go down. Goes up. On the plane, that's the prediction. But now we're going to allow for a confidence interval. So the exact prediction, what is the exact prediction? And it doesn't say. It doesn't say. However, the confidence interval is between 10,985 units of sales, I don't know, hotel bookings, and 11,528 hotel bookings. We interpret this to mean that 95% intervals of this form will contain the true value of f of x. In other words, if we collect a large number of data sets, like the advertising data set, and we construct a confidence interval for the average sales on the basis of each data set, given $100,000 in TV and $20,000 in radio advertising, then 95% of these confidence intervals will contain the true value of average sales. On the other hand, a prediction interval can be used to quantify the uncertainty surrounding sales for a particular city. Okay. So you really feel the impact of the error term when you're looking only at a specific city. If you're looking at all the cities of those in green, those error terms kind of cancel each other out. This is what they mean by 95% of will contain the true value. Now, if it's a particular city, well, there's the error term. And you know, it's going to be the error term of that specific city. Given that 100,000 is spent on TV advertising and $20,000 is spent on radio advertising, the 95%, it's a lot wider now this time. And the error term is driving this increase in width. We interpret this to mean that 95% of intervals of this form will contain the true value of y for this city. Note that both intervals are centered at 11,256, but that the prediction interval is substantially wider than the confidence interval, reflecting the increased uncertainty about sales for a given city in comparison to the average sales over many locations. So if you're interested in a specific city, then your predictions are a lot more sensitive to the error term, right? So going back to those students studying 5 hours a day, if you have 100 of them, you can get a very narrow confidence interval because you exclude the outliers. For example, that student who spends every 5 hours every day on just one topic when the exam is going to test them on 50 topics. But then if you're looking at a specific student, then that's difficult. I mean, you don't know. Am I looking at a student that is studying, okay, 5 hours a day, but then there are other aspects of their studying habits which are very different to everyone else, or the majority of those doing 5 hours a day. Just as a last 1 minute, what we'll do tomorrow is qualitative predictors. Although I wasn't look at education. Education is going to be qualitative. So look, it's so we can say, for example, anyway, we'll see it tomorrow. But these are like different education bands. Okay, and we're going to get into, I think, some mathematics. Yeah, we're going to get into a bit of mathematics now in the notes themselves. Where does this leave us? We're not quite done yet because we're going to compare it to the k nearest neighbors, but that will be probably next week. Actually, we've done really well because now chapter 4 will be very different. This will be classifying. Goes to court, does not go to court. Wins the World Cup, does not win the World Cup. Okay, this is going to be really cool. Now we're going to get probability distributions that, instead of everything we've done so far, and I mean something like this, they're going to become a two-dimensional surface. So think of your O-level histogram and kind of give it a volume instead of an area. Can we look at maybe prison incarcerations? Don't even ask me where I get these. Prison in by state. What I want is, I want something like this. But I want it three-dimensional, where they kind of place a column. if I just type 3D. Anyway, so your histogram, I didn't find quite what I was after, but your histogram is going to become like this. It's going to become three-dimensional. Number of tests, strength, whatever, right? And think of that as this. I'm actually not that well versed in. There's a really good article. If we could go back into my browser. The formula that killed Wall Street. It was actually an actuary that came up with that. The formula, or that pioneer that killed. I think it's a Wired article. Wall Street. Really famous. Oops, yeah, and Wired. Look, I don't know if I've ever shared this with you. And they actually, I think there's actually the formula. So here's what killed your 401k. 401k is like a retirement fund. They're like special tax breaks if you put money towards your 401k. Anyway, and phi has to do with the Gaussian distribution. Let's see if we type copula. Yeah. And what if we type actuary? Does actuary? Yeah, actuarial science. And this is the individual Lee. Were they a member of, or are they a member of? Let's see if they're a member of the Actuarial Society, and maybe we can look them up at some point. But anyway, so it's got a bit of bad press, if you can believe statistical distributions getting bad presses. But I'm gonna stop over here.